they are required to post on Blackboard on the discussion forum on Blackboard within 24 hours. If you miss that, you miss your attendance for that class. I just want to clarify that. If there are any confusions, please feel free to email me or my TA, Carson Stones. Our speaker next week will be Professor Greg Nemeth, who is an associate professor at the University of Wisconsin-Madison, and he'll talk to us on modeling energy technology policy alternatives using export elicitations. Today we have a very special event that happens once a semester. It's called the Student Research Showcase, and the idea here is to have a few of our graduate students, typically PhD students, talk about their cutting-edge research on energy issues from different disciplines. And we have 3 really outstanding speakers lined up for you. I'll announce your names in the order they will be presenting. The first presentation will be by Craig Andrew Milroy, who is a PhD student in chemical engineering, and he'll talk to us on lithium-sulfur batteries. Our second speaker will be Krystian Perez. Krystian is a PhD student also in chemical engineering, and he'll talk to us on smart use of smart meters. That sounds terrific. That sounds very smart. Disaggregation of AC loads from residential homes. And our third speaker will be Daniel Urieli, who is a PhD student in computer science, and he'll talk to us on a learning agent for heat pump thermostat control. And the idea of these student presentations and this showcase is to catalyze interactions, and the hope is that some of you who may not be engaged in research right now will perhaps get interested and start some of those interactions, and hopefully will take up some research. That's a very, very important component of how research and teaching go hands in hand at this university and at most universities, actually. So with that, let me turn over to our first speaker, Craig. We will have about 15 minutes for the presentation, and we will have the Q&A right following that. And so we'll do the presentations and Q&A, and then move on to the second speaker. Right?
Sorry.
Keep that on.
This is the changer. Yes. And this is
I think the laser may or not work.
Okay.
Changer will.
okay. So this just goes on. Okay. Is that all right? Okay, thanks. Okay, thanks everybody for coming today, and thank you, Professor Rai, for inviting me to speak. My name's Craig, and I'm in the chemical engineering department, and I work in Professor Mantharam's laboratory, which is the electrochemical energy laboratory. So today I was just going to discuss a little bit about some of the factors that are driving the need for improved energy storage, and then discuss some of the obstacles that sort of the most, I guess, pertinent research topics to achieving those goals, and then discuss some of the strategies that have been adopted to date to try to improve lithium-ion batteries, specifically the lithium-sulfur batteries. So this is the big picture, and I'm sure you've seen some variation of this in some form. But the 2 kind of main points here are that if you look at projected energy consumption, it's supposed to be doubling sometime in the next 15 years. And number 2, that the vast majority of that increase is going to occur in developing nations. And so cost considerations for supplying the energy storage needs are going to be very important. On the right here, the thing I want to call attention to is the fact that the renewables category, which is where a lot of the clean energy growth is going to be coming in the future, is currently a very low percentage of the overall energy that's provided, and also that these are typically intermittent energy sources. So until we can figure out a way to flip the sun on and off whenever we need to, we need some kind of an energy storage solution to capture energy for the renewables category. So then this is sort of the current state of the art. Here you can see that the lithium-ion batteries represent a pretty large improvement over previous generation batteries in terms of both the volumetric and the gravimetric energy density. And so what this means basically is that since lithium is a very light material, you can have a lot more energy per weight, and also the volumetric energy density is also large. Now this comes from the fact that lithium basically has a much higher oxidation potential, which means that you can extract more energy compared to some of these other previous generation materials. So although this is the best technology that we currently have, if you look at the sort of the needs for a number of different applications, particularly this one I just chose to highlight since this is something that's very hot right now. Electric vehicles, with the currently available technology, you have a somewhat limited range for these vehicles, and so also the cost is very high. And so people have been looking at different called next generation lithium-ion technologies in order to help improve the amount of energy that you could store and then later retrieve. And so lithium-sulfur has been one of the most researched of these technologies. And so the reason that sulfur is an interesting material, if you look here, this is capacity, which is essentially the amount of electricity that you can store in a battery. Okay. On the capacity, you'll notice a break in the scale here. Sulfur is nominally has 10 times as much capacity as the current. These are the materials that are used in the current lithium-ion batteries. So that you can see they're basically metal oxides, transition metal oxides, and their capacity is someplace around 140 milliamp hours per gram, whereas the sulfur is 10 times that. Now you'll also notice that the operating voltage of the sulfur battery is about half that of the oxide, which means that the true advantage is not 10 times as much capacity, or sorry, in terms of energy, you get about 5 times as much energy out of these. Okay. Now the other thing I want to call attention to is you'll notice here the cost involved. Okay, so sulfur extremely cheap compared to the transition metals that are the basis for the current oxide materials. So as you can see, this is just a graph showing the gravimetric power density and the energy density, and you can see that in terms of what's available today, the lithium-sulfur batteries are about the closest thing that we have to the internal combustion engine in terms of energy supply. So before I talk about lithium-sulfur batteries, I'm going to just go briefly describe the current lithium-ion batteries that I discussed. So these are layered oxide materials for the most part. This is an example of the most common lithium-ion battery right now. And the cathode is a structured layered transition metal, and then graphite anode. And what basically happens during charge and discharge is that the lithium ions here will shuttle between the cathode and the anode. And these materials were synthesized in order to perfectly accommodate the lithium that has to come in and out. So they're solid state materials, okay, first of all, and second of all, very highly conductive materials. And these are both important differences compared to the lithium-sulfur batteries. And so this is just an illustration of the charging process, and then the discharge, you can see the lithium shuttles back over. And so by contrast with sulfur batteries, sulfur is an insulator, okay, which makes it very difficult to use in a battery material where you need electrical conductivity because you're extracting the electrons out of the material to provide the energy. And so this gives rise to a whole bunch of challenges. The other thing is that whereas the state-of-the-art lithium-ion batteries are all solid state, the sulfur involves a transition from the solid form, okay, the elemental sulfur here at the beginning of discharge, will then become liquid lithium polysulfides, and then finally will become solid again, okay? Now this creates a variety of problems. Number one, you have to find some way to encapsulate the sulfur in a conductive matrix, a conductive material, and second, you have to try, if you want to retain the capacity, the full capacity of the battery, you have to find a way of preventing the migration of the liquid substances out of because they dissolve, they move out of the cathode, and then you lose that material and it's not available in subsequent cycles. And so two of the the most common configurations that we use in lithium-sulfur research. I showed the picture of the transition metal oxide. They're very highly ordered materials. In contrast with the lithium-sulfur, you typically, the first sort of generation configuration of the cathode was to take elemental sulfur, some sort of conductive material, typically a carbon, conductive carbon or a conducting polymer, and then a binder, something that just holds that all together, and then a solvent to suspend it. You try to mix it as well as you possibly can, just either mechanically or with milling or whatever, and then cast that onto an aluminum current collector, and then this is how you extract the electrons. Now, whoops, sorry. With this, the next slide will show, but this is somewhat haphazard, and so a more recent configuration has been to take a porous current collector, so some kind of a structured carbon, and then taking the liquid form of the polysulfides and seeding those into the cathode. And so this is what we call the dissolved polysulfide configuration. Now with the slurry one, what you can see here, this is just a scanning electron micrograph showing, this is at 500 times magnification, but you can see the big sulfur particles, and you can see that they're pretty well mixed, but not really. So ideally these would be completely encapsulated, and this isn't one of the best electrodes that I ever made, but this gives you an example of the problems that you get with the slurry cathodes. And you can see that even though the nominal theoretical capacity is someplace a little bit more than 1,600 milliamp hours per gram, that you get much less than that out of it, and that the capacity declines. So this is the number of cycles. This is a charge and a recharge, and you can see that as the number of charge and recharges goes, you lose a lot of capacity. So this is not a very ideal configuration. And so to improve this, people have done, and this is work from our lab. There's a lot of similar work in other labs, where people will take different ways of encapsulating the sulfur, in this case with a conducting polymer, and you just try to wrap it up as best you can. The other thing that's been done is to take another layer of carbon and insert that between the cathode and the anode, so that when the material begins dissolving, it can get trapped in between the layers. And these have helped performance to a certain degree for the slurry-based cathodes. The dissolved polysulfide, as I said, you take a structured carbon. These are These are carbon fiber paper, and then this serves as your cathode current collector, and then you seed the polysulfides into this layer. So this is not anywhere near as ordered as the other ones. And so you'll see also that there is quite a bit of capacity degradation in comparison. This is the state-of-the-art lithium-ion batteries, where you get pretty constant capacity. And so what basically happens is the active material becomes liquid, and then it is sort of sequestered away from the electrode and precipitates during discharge and is no longer accessible. So this is just sort of physically, this you can see is all sulfur. Here the carbon, you can see the sulfur is completely bonded. It's no longer in contact with the carbon. So one of the other one of the other strategies, if I come back, this is the discharge curve again. So when you start here with the elemental sulfur, you start someplace around 2.3 volts, and the first kind of change is that you go from elemental sulfur to you lithiate that sulfur, and so it's in the form of lithium polysulfides, but dissolved. And then you come down here to another solid state region where you're basically converting lithium sulfide species. And so if you say to yourself, if I hold the battery and cycle it within this range, there's no liquid, essentially. It's all solid state. And so you have something that resembles the current lithium-ion batteries, and that you're not going to have material dissolving and diffusing out of the cathode. And so if you agree to only cycle in this part, you can see that you lose nominally about 25% of your total capacity, but you have theoretically a much lower loss. And so this is a comparison. This is then the part, or the configuration where I cycle only along this lower plateau in the solid state region. You can see the capacity is lower than it would be than it is for when I cycle it through the full range, but that it's essentially constant. There you can see there's some loss, but not very much compared to the loss that you observe with the dissolved polysulfide when you cycle all the way through. So this is sort of a compromise, and this is very typical of what you face as a battery researcher, is that it's very difficult to find something where you get everything that you want. So this, we've sacrificed a bit of capacity. The performance is very constant. This is only 80 cycles now. So over several hundred cycles, we expect this to continue to perform. We have other data that shows that you would expect this to remain pretty constant over several hundred cycles. And so in terms of a long-range solution, 700 is still several times what you would expect out of the state-of-the-art lithium-ion battery. And so these are the types of improvements that we're seeking. And so, just in conclusion, the battery lithium-sulfur is a very viable technology. There's a lot of interest in this. There are actually 2 companies who purport to have commercially available lithium-sulfur batteries, but we haven't seen much besides just pure development phase work yet. So, but I know that GM is very interested in this. They've been here a couple of times and given presentations and say this is one of the more hopeful challenges. There still are one of the more hopeful technologies for vehicle electrification. However, there's still a lot of challenges in terms of the capacity degradation that you see, as well as the fact that sulfur tends to expand a great deal when it goes from the liquid back to the solid state during charging. And the anode, so what I've discussed today have been mostly the cathodes. So the anodes is another challenge that hasn't really been sufficiently addressed yet. And so I think you'll definitely see a lot more about these technologies in the future, but there's still a lot of exciting research going on. So, okay, and then I just want to acknowledge the group, Professor Mathuram, and then Dr. Fu, who's the research associate, and then my lab mates, Chin-Si, Shen-Hung, and Michael. And I'm part of the Nascent Center. I'm not sure if you're familiar with the Nascent Center, but that's what my work is covered by, and then everybody at the McCutcheon School. So thank you. Oh, yeah, sorry. Yes, sir.
So I guess the trade-off is that you have reduced capacity. Or is your team still trying to find the ultimate or the optimal combination of sulfur? Have you considered, is there like any word to include cathode technology to help increase the capacity?
Yeah, so our group focuses mainly, almost exclusively on the cathodes, okay? And so the big research thrust is that you need to have something that will encapsulate sulfur and let the lithium through. So if you could imagine a coating, I don't know, think of like a donut, and the glaze on that donut will let lithium go in and out, but not the dissolved sulfur species. So that's the general need. Now, you can see most of this has been focused on conductive carbon materials. So what I showed were just carbon powders. People are also researching nanotubes, graphene, as well as different conducting polymers. Now, there are other materials. So, for example, lithium titanate. Basically, there's a huge range of materials that people are considering. And I'd say that it's still fairly early. The carbons seem to have given the most success, but there's a lot of other materials that are compatible with sulfur that we're also investigating. So we have, there was another member who just graduated, and we just took 3 more members. And I'd say the number of publications in the area has also risen, so you'll see there are more people researching, and it makes up a larger proportion of the total research in lithium-ion. So I haven't by any means covered the full list of the materials that will be used. Yes.
So what are the competitors to the lithium-sulfide?
I'm sorry?
What are the competitors or other options that people are pursuing apart from lithium-sulfide
for lithium batteries specifically? So these, let's see, oops. Okay, so there's the ones that I know most about. Our group, we tend to be sort of segmented. There's people who are doing what would be known as future lithium ions, so improvements to the oxide materials. Because the oxides are basically, they're the state of the art. They're the big workhorse. They've been proven. They're commercialized. Everything. So there is a lot of research into improving that. These ones, people discuss lithium air, which you're using oxygen instead of sulfur as a cathode material. I don't know as much about that. The professor says, if Professor Mantharam, when he discusses this, he'll say lithium-sulfur has maybe 4 or 5 important challenges. Lithium air has 25. So he seems to be more confident that this, that the sulfur is a, and the people that I spoke with at GM called it a, what did they say? A good long shot, I guess. So, and these things, they kind of go in leaps and bounds. People say, well, there's this and that limits it, and that sort of is the conventional wisdom for a while, and then somebody finds a way around that, and it sort of renews interest. And so I think there's been a lot of interest as well in other types of, let's see, where did that one go? The capacitor, no, it's going to be down here. Oops. Yeah, so these capacitors and these sort of things that people are sort of, they're sort of mixed capacitors and batteries, and there's the solid oxide fuel cells and things. So I think, in terms of total energy provision, there's a lot of candidates. In terms of energy storage, I think, this and some of the improvements in the lithium ion are what you're going to probably see the most of. Yeah. I'm sorry? Yeah, the actual, I know that Professor Mantharam has grants with that. I know that the majority of the lithium-sulfur research in our group is actually privately funded at the present. And I know that he's been applying for other grants. So I know that it's definitely one of them. And they have an energy center that's, I think, specifically focused on that. Oh, yeah.
Okay, I don't have pockets.
I thought we were wired for that
now. Here we go. Hi, my name is Krystian Perez. I'm a second-year graduate student in chemical engineering. This is my pencil word. Glad I'm able to speak to you today. I come from IGERT, which is a group of student researchers here on campus that research the sustainable grid. So I'm going to be talking about smart use of smart meters, disaggregation of air conditioning loads from residential homes. So within the United States, a considerable amount of energy is consumed by buildings, in particular about 40%. And half of that, roughly, comes from commercial buildings, and then half of that comes from residential buildings. And while commercial buildings tends to be very predictable, residential buildings are highly variable in terms of the energy that they use. And that can be seen in this graph here. So this is from ERCOT, which is the Electricity Reliability Council of Texas. So this is the difference in energy demand between a moderate day in March and a hot day in August over in Dallas. So you can see, you'll notice that between the 2 days for commercial and industrial energy demand, there's not much of a change between the 2 days, but you can see that residential energy increases by a significant amount, about 5 to 6 times as much. And providing that extra peak energy requires a lot of additional infrastructure in terms of the electricity providers, and it can also cause problems such as brownouts and blackouts when that demand can't be met. Even looking at it dynamically, so this also comes from ERCOT from last week. So you can, on the x-axis here is the time of the day, and on the y-axis is the amount of energy that's being demanded at any time. So you can see that It's low during really early morning hours. Then around 7 or 8, everyone makes their Pop-Tarts and then goes to work. And then you have a peak demand later in the day. So the problem isn't during these low period times. It's when you have peak demand that electricity providers have to struggle to provide that electricity. The electricity that's powering these lights and this TV and this computer right now is being produced at this very same moment. So being able to not only predict but be able to match that demand is the challenge for electricity producers. And finding ways to lower that peak is one of their challenges. So I just told you that residential energy is highly variable, and so is the amount of electricity being demanded. So my question to you is, for an average home here in Austin, what are the top energy consumers within the home? Any ideas? Climate control. So AC, you guys went for it, big money. AC consumes about 40% of your electricity. You can tell that because when it's hot, anyone who's paid their electricity bill these past couple months has definitely noticed how much it's increased. Any idea for the other two? Just by chance? Oh, what was that? Refrigerator. Actually, refrigerators only take about 4% of your electricity in your home. It's not a very large load. Oh, yeah. You got it, number 2, water heating, having your hot showers in the morning. And then the last one, which I have a lot of here, is lighting. So being able to understand how residential energy changes in response to external factors such as weather, especially your air conditioning load, is a really important topic to be able to address, to find ways to mitigate or lower that peak load. And UT Austin is uniquely positioned to answer that question through the use of smart meters and data mining. So smart meters are meters that are installed in a home. They communicate electricity use data in real time to the electricity providers. So with the Energy Independence Act of 2007, a lot of smart meters were able to be installed, especially within the residential community where that load was not previously known. Before, electricity producers would install it in large industrial consumers. And then from that, not only could they match the load a lot more easily, but that they could also develop strategies for if there's a peak day, they could incentivize to lower the electricity in that industrial sector for a little bit to be able to prevent blackouts or brownouts. So being able to understand it in residential homes hasn't been available until very recently. In particular, Austin is special because we have the Pecan Street Research Institute, which has outfitted 2 neighborhoods here within Austin. The Mueller community, which is about 2 miles north of here, and the Great Hills neighborhood, which is about 5 miles west of here. So those homes have been installed with smart meters that communicate real energy data in 1 second to 15-minute time intervals. Mueller district in particular is really interesting because it has a high penetration, this is a picture down here, of photovoltaics on a lot of the homes, as well as early adoption of electric vehicles. So data mining, the phrase data mining refers to pulling out golden nuggets of information from this large data set. So hidden within all this data is insights into residential energy behavior, how they react in response to external factors, and then from that being able to develop models of how an entire neighborhood will respond, and then being able to investigate alternative strategies to lower peak demand, such as thermal energy storage or district cooling. So that being said, this is an example of smart meter data. If this was installed in this is the typical home in the Mueller district, and this is reported in 1-minute time intervals. So on the x-axis here is the time period, going from midnight to midnight, and on the y-axis is the power demand. So you can see that something's cycling on and off in the morning, then apparently someone left, and something cycling in the afternoon, and at night something turns on a lot and then cycles on and off. So we talked about how AC is a significant portion of how much electricity you consume. So if this is the output of a typical smart meter, hidden within this data set is information on your AC load. And so the challenge is being able to pull out information on that AC and then being able to find modeling strategies to show the changes that come from that. So the way that I do this in my research is through a method called non-intrusive load monitoring. Non-intrusive refers to the fact that No additional wiring or installation is required, just the original smart meter. And load monitoring, meaning I'm pulling out the electric loads from there. So the premise of what I do is that, especially for cooling climates like here in Austin, the AC load is a significant portion of that overall energy profile. So I'm going to be using a training period of the early morning hours when the biggest factor is your AC turning on and off, to be able to develop an algorithm that for any home, a generic algorithm, can pull out information on your AC load. So I'll use this training period of the first couple hours in the morning, and I will cluster the difference in energy, cluster meaning group, the difference in energy between any of the peaks. So I'll have a cluster of on switches that signify that the power jumped up, meaning the AC is cycling on, some nominal values of where it stays about the same, and then where it jumps down when the AC turns off. So using that information, I'll get some key parameters specific to different homes, and a couple other parameters that will help me really pull out the AC use in order to estimate what AC use is going to look like throughout the day. So, while most meters are just report the overall energy use, some of the homes within the Wakan Street Research Institute were outfitted with sub-meters, meaning they were directly measuring the AC. So I use this to validate the results of my my algorithm. So on the top in blue, you see the overall energy use. This is on the x-axis is the day during the year, going from July 2012 to July 2013. On the y-axis is the amount of energy being demanded. So below the blue line, you have estimated and true, or you have true AC load in green dashed lines, and red is the estimated. And you can see that they match very closely. Down here is an example of a parity plot. The parity plot, you plot the true value versus the estimated. And ideally, if I perfectly predicted everything, it would be on that straight line going 45 degrees. But you can see that it stays consistently there. So the algorithm worked particularly well for this home. I also had 17 other homes. And the R-squared value, which is an estimate of how well or how accurate you are, was about 0.9 out of 1. Led me to validate that my algorithm was working correctly for these homes that had been sub-metered. So I extended it and applied it to 88 other homes that had not been sub-metered. So while these homes are nice because you know exactly what the AC is, being able to pull it from a general energy profile was an important part to be able to estimate. Now let's look at how does a neighborhood look in response to energy use. So I'll show you some of the results that I found. So were we just to use sub-metering data, this is the average energy that a home consumes during a day. So I should explain that on the x-axis here is cooling degree days, which is a measure of how hot it is outside. So you can think of this as mild versus hot over on the other end, and then the amount of energy. So while this information is useful to maybe an electricity producer, because they can just tell how much is being pulled at any particular time, there's not a lot of wealth information of, it increases, but what's actually increasing. So using the disaggregation technique, I pulled out the information on AC load and pulled out what your actual AC is. So the green dots on the bottom down here is your average AC consumption, and the red is the non-AC load. So you can see that there's a definite increase in slope between, for the AC load, between a mild day and a hot day. And it contributes to the difference between a mild day and a hot day for your total energy consumption. The difference there, about 65% of that is just coming from your AC unit. You can also see that the non-HVAC energy is increasing, and part of that is when it's hotter, people tend to stay home, and they start to use alternative methods to cool their house down, like fans and stuff like that. So that's one example of stuff we can't, that was previously unknown because it wasn't worth the economic benefit to really measure individual homes. So that's one example. Just looking at peak time, defined by, for example, Austin Energy is between 2 and 8 p.m. when energy consumption is already the highest. Just looking at how much that energy increases between a cool and a hot day is shown by this plot right here of cooling degree days versus peak energy demand. So the increase here of about 10 kilowatt hours contributes to about 30% of that total increase between a mild day and a cool day, or a mild day and a hot day in terms of your total energy consumption. So in particular, that peak time between 2 and 8 is where the real crux of peak demand is coming from. So finding alternative methods to be able to provide that cooling is of interest to electricity producers as well as researchers who want to use a better model to be able to figure out, well, how do we provide that same amount of cooling and lower this demand here? And I'll just show you one more plot because I think I'm running out of time. But let's go here. So we'll just look at the AC fraction of total energy. So this is a box plot. The median of the data is the red line in the middle, and then the box signifies 50% of the data. So you can see that a lot of the homes lie within a narrow band. As temperature increases, the amount of the fraction of total energy that is AC is starting to increase, and then it kind of levels out. Part of that being because HVAC units are designed to only handle a certain amount of cooling load. So you can just noticing that the homes are distributed narrowly leads us to think that a lot of thermostats, for example, in a home just comes as is, and people leave it that way. So the same way that it was programmed when you bought the house is the same way you leave it. So being able to understand that and how many homes are acting that way, and being able to evaluate other ways of providing that cooling energy. So I guess in conclusion, I showed that, let's go back. I showed that I was able to develop a general algorithm to be able to pull loads from AC use. And then from that, my hope is to be able to develop more accurate models of how an entire neighborhood responds in reaction to external temperatures, particularly temperature on your AC use, then being able to evaluate different strategies of being able to level that load. There's some acknowledgements. The IGERT group that I come from, the research group that I come from, Edgar and Balde, and all the student researchers in there, as well as Dr. Novoselic in civil engineering, and NSF. Thank you. Do you have any questions? Yes. Oh, microphone. Sorry.
So, I remember the Texas legislature passed a law, and I just wasn't familiar. I can't remember what it did, but I know it had something to do with smart meters this past legislative session. I didn't know if you had any idea what the legislature did. It was some sort of authorizing legislation for utility companies.
I'm not super familiar. A lot of homes here have already actually been outfitted with smart meters. And part of that is if you ever, when you were younger, if you remember someone coming around and checking your electricity meter to figure out how much electricity is being used. So replacing that labor need by smart meters is one thing that's happened and is a benefit to electricity users. But then that also prevents them from getting, for example, sued. That was where a lot of economic benefit came from. People were like, I didn't use that much electricity, so they tried to sue the utilities. So this is a very accurate way to be able to keep that. But I'll look into that. Yes? Either way. Ladies first.
I was wondering, how does this compare with energy use? Did you adjust for socioeconomic quantities of the house or income or something like that? I mean, I know it was for neighborhoods which are probably pretty similar in general if people live there, but do you do any sort of study of that?
Not quite yet. So the purpose of my research was primarily to develop that algorithm so that now smart meters are being mass installed in a lot of different places. So particularly Pecan Street is going to be installing meters in an apartment complex that's low income. So understanding how electricity use changes, human behavior influences a ton, right? If you insist that your house is cool and that you have really high thermal comfort, then the way that you use electricity is going to be different for other people. But that is, I hope, something to investigate, yes.
Thank you for your presentation. It's very interesting stuff. I know you can't speak for the entire field of research that you work in as much as I'd like you to, but is your ultimate objective to come up with a similar sort of algorithm for all sorts of electrical loads in the home, or is this have a much more narrow focus than
I'm primarily concerned with AC use because it's such a dominant feature. That being said, there's a lot being done in non-intrusive load monitoring. some people are like want to be able to figure out if you turned on the light bulb upstairs in your room or the one downstairs, and that can get very like 1984-ish. So security reasons for that. But the purpose for me was to be able to develop better models to be able to find strategies to meet that EC load. Mm-hmm.
So whenever you develop your model, do you make a certain margin in order to say, okay, for sure, if the power company makes this amount of energy, that it's going to cover everybody?
Maybe I'm not understanding the question.
Well, I assume that the end goal would be so that the power company can use this data in order to make enough power to support the houses.
Mm-hmm.
Power.
Oh, yeah. So that's one purpose that, like they already do that. So one unique aspect of this is that the data is collected in very fine time intervals, so 1 minute in terms of mine. A lot of utilities are doing it in 15-minute in terms of like residential homes. So they are meeting it and being able to meet that demand really well as it is. All right, thank you. I'm not sure. All right, thanks. Oh, and this.
We have the microphone here, right here.
Okay, thank you. Hi, thanks for having me here. Does it sound okay? Yeah. Hi, my name is Urieli, and I'm going to talk about the learning agent for heat pump thermostat control. This is joint work with Peter Stone here at the UT Austin. So to motivate my work, this is actually very similar to the previous talk. We look at the Building Energy Data Book that is published by the US Department of Energy, and there we can see that 40% of the energy consumed in the US is consumed by buildings. And out of that, again, HVAC systems, air conditioning, heating, ventilation, and air conditioning system consume about 50%. So if we're able to save energy in HVAC system, this could be a large portion of significant energy saving with respect to what is consumed in the US. So in this work, we focus specifically on a specific type of HVAC system called heat pump. So some of you might be familiar with it, but I'll just give a quick intro. So heat pumps is a popular system that is very efficient and is widely used. It can produce, the heat output it produces can be 3 to 4 times the energy it consumes, and the reason is that it doesn't, instead of converting one energy source to heat, it actually moves heat from hotter places to cooler places. And another advantage of heat pumps is that they consume electricity, so therefore they can use renewable energy resources. However, heat pumps also have drawback where they are no longer effective when it gets very cold outside. This is why they are backed up by auxiliary heater, which is typically a resistive heat coil. And the resistive heat coil is unaffected by outside temperature, but it consumes twice the energy consumed by the heat pump. So therefore, it's best to minimize usage of the auxiliary heater as much as possible. So coming from artificial intelligence perspective, we're interested in decision making, and the heat pump heat pump system decision maker is the thermostat. So we all know that thermostat controls comfort at home, but it turns out that it also has a significant effect on the energy consumed at home. And there is current interest in smarter thermostat that is evident by the appearance of startup companies like Nest, as well as thermostats produced by traditional companies like Honeywell. For example, this is an example of smart thermostat produced by Nest, and this was actually one of the most popular Christmas presents in one of the recent Christmas seasons in the US. Some call it the iPod of thermostats because it might remind an iPod, and it was actually designed by the original iPod designer, so you might find some similarities. Anyway, here our goal is to minimize energy consumption while satisfying comfort requirements for the occupant. And the contribution of this work is we introduce a complete reinforcement learning agent that learns and applies an adaptive control strategy for a heat pump thermostat. And our agent achieves in simulation between 7 to 14.5% of yearly energy savings, while still satisfying the same comfort requirements with respect to the strategy that is actually deployed in practice. So for this work, we use a simulation environment called GridLabD. GridLabD is an open source simulator developed for the US Department of Energy. And specifically for our purposes, it has a realistic model of residential home, which includes heat gains and losses, the effects of thermal mass, solar radiation, and it uses real weather data that was recorded by the National Renewable Energy Lab. And this is so next I'm going to define our specific problem setup. So we simulate a typical residential home, and the goal is to minimize the energy consumed by the heat pump while satisfying the following comfort specifications. So the x-axis is the time of day, this is 24 hours, and the y-axis is temperature. And specifically, since this is a residential home, we assume that occupants are sleeping at home during night, then they leave to work or school, and then they come back during the evening. So whenever occupants are at home, we require the temperature to be within some comfort range. Here specifically, this is 69 to 75, but this would be any range. And during the day, any temperature is okay. So we call it the don't care period. And the goal is to minimize the energy while satisfying this comfort specification. So let's look at how the default thermostat works, and it's very simple. It has some upper and lower bound for the temperature requirement, and wherever temperature leaves this comfort zone, it actually brings the temperature back by heating or cooling. So this is an example of the default thermostat operation over a 24-hour period, and we see that this is a winter day, so temperature drops, and then the heat pump is used to bring the temperature back to range. It works well for some time, and then it gets colder outside, and the heat pump no longer works. And temperature, despite the heat pump is working, the temperature is still dropping. So when it crosses an additional temperature buffer, the auxiliary heater kicks in and eventually brings the temperature back to range. So a natural question to ask, we want to save energy, so can we just shut the system down during the day and then turning it on when occupants are back at home? So simulating it, we actually found that this strategy consumes more energy than just leaving the system on all day. And the reason is that temperature drops very low, and then the auxiliary heater kicks in and consumes a lot of energy trying to bring the temperature back. In addition, we also don't satisfy the comfort specification since it takes several hours for the auxiliary heater to restore the temperature. Here it actually, after 6 hours, it is still out of range. So therefore, people frequently prefer to leave the thermostat on all day, but it makes sense that there must be some smarter strategy that turn off the system for some time and then heat or cool in advance and achieve some energy saving. And this would be our goal here. So to further motivate our work, we can look again at the US Department of Energy website, and under the section of heat pump tips, there is a bullet that says do not set back the heat pump thermostat manually if it causes the electric resistance heating to come on. So this is exactly what I was talking about. And in another place, so programmable thermostats are generally not recommended for heat pumps. from the same reasons. So this is a real problem. Here I list the challenges of solving the problem. I won't go over all of them here, but just briefly. So we can look at it as follows. So we can think of some imaginary line where as long as we are above this line, we are able to heat the home and restore the temperature back to range on time. If we are below these lines, we are no longer able to do so. But this line is unknown in advance. It depends on unknown future weather, and it also depends on different home. For example, if you have a larger home, you need to start heating longer in advance. If you have a smaller home, you can wait a little longer. And we want to design a general algorithm that is able to adapt, to be deployed in a specific home, adapt to the home properties, and being able to predict this line and affect it and heat in advance exactly as late as possible to save energy, but still recover the temperature. Some other challenges here is that, so we have a learning agent, and whenever we have an agent that needs to learn something, it needs to explore the effect of its actions. So if it heats for 5 minutes, what would be the temperature difference? How in a winter day it's going to be different than summer day. But in this setup, we want to be realistic, so we cannot let the agent explore arbitrarily. For example, we don't want it to try random actions for 1 month. So we're limited in the way we are able to explore. So I'm not going to get into the technical part here, but just briefly, we model our problem as a Markov decision process, MDP. And briefly, MDP has states, action, transition, and reward, and terminal states. And the idea here is that at any given moment of time, an agent is at specific state of the system, and then it needs to take some action. This action might land him in the next state, and there might be some stochastic noise, and there is some probability distribution over the next state it's going to be in. And every such transition, it also gets some reward or pays some cost. So reward and costs are the same. Reward is minus the cost. So you either want to maximize reward or minimize the cost. And there are some algorithms to solve MDPs, finding the optimal decision making. But here, our MDP has high-dimensional continuous state, and therefore we need to use specific methods to solve it. So skipping over the technical part, I'm taking you right to the final slide of the MDP. And okay, so our actions of this MDP is just the thermostat actions. It is either cool, off, heat, pump, heat, or auxiliary heater. The reward function that we try to optimize contains some penalty for using energy and for not satisfying the comfort specification. We define our states in such a way that the state contains enough information to allow us effective decision making. And I won't get into how to do it now. And the transition function, meaning the effect of my actions, heating or cooling, this is going to be learned by our agent from experience. And this is what gives our agent the flexibility to adapt itself to any new environment. So, yeah. Okay, so briefly, our agent operation goes as follows. For 3 days, it just randomly explores the effect of its action. So it can be in arbitrarily high or low temperature as it's possible. And then, starting day 4, it starts to execute an energy-saving setback policy while still improving its model and improving its policy. So exploring for random exploration for 3 days, there are some more advanced exploration strategies. However, we still believe this is a realistic setup. For example, we can send the home occupants for a weekend vacation, and then our agent can learn how the effects of its actions work. But there are more advanced exploration strategies if one wants to use them. In order to execute this energy-saving policy, the agent do something like model predictive control or look-ahead policy, where it just simulates keeps simulating the future and choosing the most promising action. So next, some results. So we simulate 1 year under different weather conditions. We simulate 21 residential homes of sizes that range between 1,000 square feet to 4,000 square feet. And we use real weather data recorded in New York, Boston, and Chicago. And the reason we use cold cities is because heating consumes much more energy, and therefore there is larger potential for energy saving there. So these are some snapshots of how the final policy looks like. So again, the x-axis is the time of day, and the y-axis is the temperature, and these are winter days and summer days. This is mild days, and this is more extreme days. And we see that in every summer, winter, mild, or more extreme, our agent knows to set back the temperature, turn off the system, and then heat in advance, choose the right heating point to restore the temperature back to range. These are our energy savings. So here, these are the house size between 1,000 to 4,000, the x-axis, and the y-axis is the energy savings, and each of the plots is New York, Boston, and Chicago, and we see that in general our agent is able to save between 7 to 15% with respect to the strategy, again, that is actually deployed in practice. And we also see that we also satisfy our comfort requirements. So this is the result of more than 22,000 simulated days. And what we see is the temperature histogram of the temperatures at 6 p.m., the end of the don't care period where occupants are at home. And we want the temperature to be somewhere here, and we see that most of the temperature are within range, and those that aren't are off by maybe 1 degree Fahrenheit. So the comfort requirements are mostly satisfied. So to summarize our work, we present a complete adaptive reinforcement learning agent for controlling the heat pump thermostat, and the techniques we use is to carefully define the problem as an MDP, Markov decision process, and then use some advanced reinforcement learning methods to solve it. And we ran experiments over a range of homes and weather conditions, and our agent achieves in simulation between 7 to 14.5% of yearly energy savings, while still satisfying the comfort requirements. Thank you for your attention, and I'll be glad to take any questions. People ask me about it and told me to think about the poor pet. So yeah, it is possible to add additional constraint because we keep simulating the future from any given point. We can add a constraint that you don't want to go below some temperature, and wherever you get close to it, you just heat or cool, not to cross some threshold. So yeah, it's not too difficult to incorporate to this setup such constraints.
So does this require any inputs like real-time weather data, or kind of what goes in, or does it just figure it out on its own?
Yeah, so this is part of the technical part, which I skipped. But yeah, we use a weather forecast to help us predict what would be the actual slope when we heat or cool. So yeah, we need this information, and all of it is encapsulated in the state of the MVP.
Yes, I was just curious, what were the main factors associated with not achieving, when you were looking at the reward function? What were the factors that were primarily responsible for not achieving the desired temperature? Do you stratify your analysis by building material type or
I'm sorry, I didn't get it. So the main factors in what?
Yeah, so you have your reward function involved whether or not, it looked like the chief factors, whether or not you achieve the desired temperature at the arriving home time. And I was wondering what factors besides the exterior temperature were associated with that. Did you look at building materials or the home type, or?
So if I get a question correctly, so our agent, so you can deploy it in different homes, and each home different materials. All of this can be encapsulated in the transition model. So if you heat for 5 minutes, home with, I don't know, wooden home would respond differently than other types of home. And this is what is exactly being learned by our agent to learn the effects of its action. For example, if I cool for a few minutes or heat, what would be the temperature difference and things like that. Does it answer the question?
Exploration period, you're setting your trying to put the betas in your model, the effect of turning it on and off.
So exploration is taking actions like heat or cool or auxiliary heat and recording the differences between the temperature before taking the action and the after and things like this kind of information.
Sort of calculating the transfer functions.
Yeah, the transition function.
You're out of time. That's kind of what we're doing.
Thank you.